the better part of the next hour with a visiting speaker from the physics department. The bad news depends on how you feel about listening to someone talk about antimatter and discussing something about antimatter. But first, this is our relaunch of Science Cafe. We used to do this at Borders for a couple of years. This was originally launched by Erica Big Ali. She did a great job getting this all together. And it worked very well until the fateful day that Borders closed. And so we were without a home, and we got a little disorganized. So we're just now getting back on relaunching Science Cafe in this wonderful space. So I would like to start by thanking some people who've sort of made this possible. The volunteers that helped put this together. It's a lot more work than one might think. Websites and flyers and distribution and all that. So a lot of people have put an effort into making this happen. I'd also like to thank the owner and staff of Rachael's Cafe for making this facility available to us. It's a great space. I think we'll do very well here. I remember there are lots of science cafes. There are probably 200 of them in the US, and they're all over the world. The one in Seattle is in a pub, and it's called Science on Tap, and I was always very envious of that. I thought, wow, that's really cool. But we kind of have the best of both worlds here. We have both coffee and beer and other things. So this is, I think that really promotes kind of convivial and introspective atmosphere. So I'm very appreciative of Rachael's Cafe for allowing us to do this, and I encourage you to take advantage of what they have to offer. And then thirdly, I'd like to thank both our current speaker, but also our future speakers. So there are a lot of people who have agreed to speak. We have a great lineup. We have topics such as the science of addiction. We've got Ben Rapson's going to be talking about climate change in Bloomington, and the potential impact of climate change in Bloomington. An example of brain-machine interface in the form of eye tracking. One group is going to be talking about that pair of graduate students. And we've got somebody who's going to be talking this winter who's involved with the geology department, involved with the Curiosity rover on Mars. It's going to give us an update this winter about what's been going on with that. So this and many other things that we're going to be talking about. And so we're very excited about the lineup and about the future of getting Science Cafe off the ground and keeping that way. So enough of that, though. I would like to introduce our speaker. This is Dr. Snow, Dr. Mike Snow, with the physics department. And he's graciously consented to be our inaugural speaker. So he graduated in 1990 with a PhD from Harvard, and then went for a postdoc with NIST in Maryland, which I hear is a nice place, and went there for 3 years, and then came here directly. So he's now a professor in the physics department in experimental nuclear physics, and has agreed to tell us a little bit about antimatter. And so the format, I think you're going to be talking for about half an hour. I don't know how comfortable you are with people asking questions during the talk, or if you want to save it for afterward. But the idea is that this should be interactive, and we're leaving a lot of time for questions afterwards. There's an opportunity for discussion as much as hearing someone talk about a topic of general interest related to their work. That's the idea. So with no further ado, I introduce Dr. Smith.
Okay, is this good volume for people? Can you hear me? Okay, so I'm going to talk about antimatter. And I'm just going to, I imagine I'm going to speak for, roughly speaking, a half hour or so. And I thought about what I'd want to say about antimatter. And I've got 3 topics in mind. And so let me just write down what the topics are. And I'm going to try to talk about it. So the first topic, keep it from falling. So the first question is, what is antimatter? Actually, first question I have for you. How many people have heard of the phrase antimatter? The second question is, do you know where you heard it? Yeah, where?
Documentary about
Okay.
Star Trek.
Star Trek. For the older people in the audience, definitely, and that was true myself as well. I first heard of the word antimatter in Star Trek. Other people, have you heard of the word antimatter in other places? Those are two, obvious ones. Okay. So I'm going to try to explain what it is. That's number one. Okay. Number two, I'm going to say a little bit about how it was discovered. Okay. And I want to say a little bit about this because there was something historically very unique intellectually about its discovery. And so I'll say a little bit about that. It turns out that it was the first time that a new form of matter was predicted before it was seen in experiments. In other words, it was predicted on intellectual grounds that it must exist. And then you looked and you found it. Before this discovery, it was always the other way around. You found stuff and you discovered matter, and then tried to figure out how to fit it into a theory. This went the other direction, and it's extremely interesting. And that's the way many discoveries are made today. And then the third thing I want to talk about is, well, maybe four things. I've already added a topic. I think I'll say a little bit about antimatter in your life. Okay? For example, right now, I can guarantee you there is antimatter in this room. And it's quite possible that you have had a medical procedure that used antimatter. So it's quite possible you've actually used antimatter for something that keeps you alive. And then finally, I want to say a little bit about antimatter in the universe. Okay? Because there's something very peculiar about the universe that we don't understand. And it's, the way to simply say the situation is that we don't seem to see very large clumps of antimatter in the universe. And we don't understand why. So there's a huge mystery in the universe about antimatter. So those are the four things I want to talk about. Okay? And before I start to talk, do people have any questions? I can start to talk, and you can start to ask questions. It's fine either way.
When are you going to tell us where it is in the room? Are you hearing it?
I don't know where, okay? But I know why it must be in there. Okay? The reason is that coming from outer space, we have extremely high energy particles that are striking this room, and they have enough energy to create antimatter. And given the number of particles per second that is hitting us and their energy, I don't know where the antimatter is in the room, but I know it's here. Okay? And there's another source of the antimatter, and that is that a small part of your body, just the atoms and the nuclei in your body, are unstable. They're radioactive, very slightly. And some forms of radioactivity make antimatter. So there's probably antimatter in your body right now. So those are the two sources that I know about that exist. But I can't point to you and say the antimatter's right there. Some other questions? Yeah?
Does antimatter exist indefinitely, or does it have a little lifespan?
Okay, so I'm going to answer that question by talking about topic number one, what is antimatter? Okay? So let me try to set the stage. In our theories of physics, there's a way to make a division of all the stuff we know into 3 piles. Okay? One pile of concepts is what we call space-time. And if you want to make the analogy between a play and the laws of nature or the universe, space-time is the stage. Okay? It's the framework within which other things move and act. Okay? So that's one classification of stuff, space and time. Okay? Then there's 2 other classifications. One's called matter. And loosely speaking, the way you think of matter is stuff. Your matter. Okay? Then there's a 3rd classification, which is the forces between matter. Things like gravity, things like the electrical force, the magnetic force, and there are a few other forces. And so those objects, the things which transmit forces, are kind of think of them as a 3rd pile. Okay? So now I'm going to start to answer your question. Okay? So the first thing to understand about antimatter is that in this group of 3 piles, antimatter is in the matter pile. Okay? And this is a common situation in physics, in the language we use. If you just think of the meaning of the prefix anti, your first thought is antimatter is against matter, or it's the opposite of matter. But that's just a typical problem in the use of the English language to describe something in nature. Right? Really, antimatter is just a type of matter. Okay? So that's the first thing to understand about antimatter. So if it's a type of matter, what is it? Okay. So maybe I'll give you another question. What comes to your mind when you hear the description of the word antimatter? What do you think about it?
Black holes.
Black holes? Yeah.
Explosions.
Explosions. Why do you think of explosions?
Oh, it's when antimatter. This is how the Star Trek drive works, right?
Oh, that's right. It's causing explosions all the time. That's actually a good thing to keep in mind, because it is true that if you bring antimatter and matter together, there is a tremendous release of energy and an explosion. Okay? So now coming back to your question, it is true that if I have antimatter close to matter, it's in danger of disappearing. Because what it will do is typically the antimatter will attract the matter, they'll come together, and when they come together, often they can disappear into pure energy, and then it's gone, with a large release of power.
So where's the explosion?
Say what?
Where's the explosion?
Well, it depends on how much antimatter you have combining together at the same time. Right? If you've got a gob of it, twice the amount of antimatter makes twice the explosion. Okay? I should say, on the Star Trek business, nobody has isolated a huge amount of antimatter in one place. Typically, we can only catch antimatter in single particles, or maybe a small collection of particles. Okay? It's very difficult to accumulate a huge amount of it. Very difficult. So I'm sorry, Star Trek is orders of magnitude away from what we can imagine doing. So it is true that if I bring matter and antimatter together, they do annihilate. But there is a way I can hold antimatter and not have it go away. And it turns out that if I hold it with these particles that transmit the forces, like electric fields, magnetic fields, gravity, that doesn't annihilate the antimatter. So it is possible to have a piece of antimatter which you isolate from everything else and hold with electric and magnetic fields. So it is possible to hold antimatter with something that you're touching, but does not annihilate. It's not easy, but it can be done. The word anti makes you think about the matter having opposite properties, the antimatter having opposite properties to the matter. Okay? So, for example, you may know that many objects have a property called electric charge. So, for example, an electron has a negative electric charge and it makes fields which influence other objects with electric charge. Antimatter has the opposite electric charge. So if you've got an electron, right, and people usually use the symbol running out of stuff here. Oh, that's gone. Ignore that. If I have an electron, there is an antimatter twin of the electron called the positron. It has exactly the same mass as the electron, but its electric charge is opposite. Okay? Likewise, the proton, which is inside the nucleus, there is an object called an antiproton. It has exactly the same mass as a proton, but with a negative electric charge. A normal proton has a positive electric charge, an antiproton has a negative electric charge. And as you know, opposites attract. So if I have a piece of matter and a piece of antimatter, the electric charges will cause them to come together, and then they'll be close. There was a question.
What happens to the neutron?
Very good question. It turns out that there is such a thing as an anti-neutron. Okay? Now, here's the trick. There's a trick involved. You have to invite me back to talk about quarks. So it turns out that the proton is itself not a so-called fundamental elementary particle. It has got charged particles inside of it. Okay, so the neutron is actually a bound configuration of 3 objects. And those 3 objects have electric charge. Okay? It turns out they're called quarks. And there's 2 down quarks and an up quark. The down quark has a charge which is 1/3 E. And the up quark has the opposite charge of 2/3 E. And so you get 1/3 plus a 1/3 minus 2/3 is 0. Okay? So the neutron is electrically neutral, as you said. But if I change all of the quarks to anti-quarks, then I have a different object, because inside I've got an anti-up quark and 2 anti-down quarks. So just because an object is overall electrically neutral does not mean that it doesn't have an antiparticle. Another example is the hydrogen atom. You may know the simplest element is hydrogen, right? And a hydrogen atom is a positive proton with an electron around the side. Right now, as I speak, people are trying to create anti-hydrogen, which is an anti-proton in the nucleus and an anti-electron on the outside.
Why are they doing it?
Say what?
Why are they doing it?
So why does antimatter exist?
Why are they looking to make the anti?
I see. Okay. The reason is the following. First of all, it's cool. That's one of the first things you have to understand about physics research and scientific research in general is that one of the motivations is because it's neat. The other motivation is that we want to use that matter to test whether or not our laws of nature are as perfect as we think they are. Okay? So you may know that a hydrogen atom, like many atoms, has a set of energy levels, and that when an electron around the proton of the hydrogen atom changes its condition, it can radiate light. Okay? If our theories are correct, an anti-hydrogen atom is supposed to have the identical energy levels and it should radiate the identical light. That's our theoretical prediction for what should happen. So we want to check it. If it was different, the laws of physics would be seriously in trouble. Right? So that's the reason why I want to make this antimatter, is just to check out the laws. Let me say a little bit about how antimatter was discovered, because it was a strange story. You may know that in 20th century physics, there are sort of two super big ideas. One, I would say, is quantum mechanics, which describes the true motion of objects in strange ways. And that would be a good subject for the Science Cafe. And another big idea is Einstein's theory of relativity. And historically, both of those ideas sort of started to develop around the mid-1920s. Is when, well, Einstein's a little bit earlier, 1905, and then in the mid-20s, people started to invent quantum mechanics. So when you develop two fundamental ideas like that, the obvious thing for a theoretical physicist to do is to put them together and see if you predict anything new. Okay? So if quantum mechanics and relativity are both true, what is the consequence? Okay? So the first person to do this was a guy named Paul Dirac, who was an English theoretical physicist. There is a legend for what happened. He was at Cambridge. Very interesting guy. He got his bachelor's degree in electrical engineering because his father wanted him to be a practical kind of guy. Well, as you know, that never works out. This guy had a passion for science, and he was in the middle of all these new ideas and trying to figure them out. He was sitting in a room in Cambridge staring at a fire. This is the story he tells. He was staring at a fire, and he suddenly realized, oh, I want to do this. I want to add this thing to my equation to make something work out. And he did it. It's too technical to explain the details, but he did this procedure. He realized, dang, I want to do this. He went down and did it. He wrote out his answer, and his answer forced him to add an antiparticle into the equations of his physics. And for a while, he resisted the conclusion of his own work. This is also very common in physics. Sometimes we put theories together, and then what we should do is just take the conclusion of the ideas all the way. Just what's the answer if I take these ideas seriously? And many times in the history of physics, people do this. They write down, but they don't believe it themselves. For example, the expansion of the universe is something Einstein came up with, but then he scratched it out because he didn't believe it. Dirac had a similar reaction. He said, my God, this new equation I've written predicts a new form of matter with the electron having an opposite charge, i.e. antimatter. He just didn't believe it. But he was the first person to have the courage to say, it's so beautiful, it must be true. And so he said, all right, I add these two ideas together, relativity and quantum mechanics, it predicts a new form of matter that's never been seen before, it therefore must exist. So he predicted, and that was a unique thing in the history of physics. So then when he predicted it, of course, the other subset of physicists, the experimental physicists, tried to find it in the laboratory. And they found it within 2 years. It turns out that people had already seen antimatter in experiments, but they had not interpreted their data correctly. And this also happens occasionally in the history of physics, is that the experimentalists will be slightly influenced in the interpretation of their data by what the theory says ought to happen. Okay? And that was true in this case as well. Nevertheless, after Dirac made this prediction, very quickly an experiment said, yes, I see this object. It has exactly the same mass as the electron, but the opposite electric charge. It's antimatter. And
So the first antiparticle was a positron to be discovered?
yes, that's right. And there's a reason why that was the first thing discovered, the first piece of antimatter, is that it's the cheapest from the point of view of making it. Okay? So as you may know, electrons are relatively light as far as their weight goes. And for example, a proton is about 2,000 times heavier than an electron. So if I'm going to try to make an antiparticle, I have to supply enough energy to create it. And as you know from the equation E equals mc squared, the higher the mass, the more energy I must supply. So you would expect that if you're going to try to make antimatter, the easiest stuff to make is the light stuff. And so the first thing to be discovered was the positron. And then later, the antiproton was made, maybe 20 years later or so. And since that time, every object that we've discovered has its antimatter counterpart, without exception. So that's kind of the discovery. Yeah, question?
Does theory predict how much antimatter is in the universe? Are there large pools of antimatter, or is it very rare?
Yes, very good question. The answer is no. That's really not predicted in a rigorous way. But it's very interesting. And that's kind of my subject number 4. Let me say a little bit about that. So here's a funny thing about antimatter. Okay? I was telling you earlier that if I compared the light from a hydrogen atom with its proton and electron to the light that would be emitted from an anti-hydrogen atom with an anti-proton and a positron, that the light energies would be identical, and therefore the spectra of light would be the same. Okay? Therefore, imagine you're searching for antimatter in the universe, and you are an astronomer, and you look at the light from a galaxy. Okay? And you look at what astronomers do to figure out what the matter is far away is they look at the spectral lines, and they try to match them to elements that are known on Earth. And so far, they all match, by the way. All the matter that we can see in the universe, we seem to have the same stuff here as is out there. But if you were looking at an antimatter galaxy, you cannot tell from the light if it's antimatter or matter, because it radiates the identical light. So the first answer to your question is, we don't really know. Right? We can't. It's not easy to tell by looking. There's a question here? Yeah.
Would the anti-elements have the same stability, radioactive stability as the elements? Same half-time?
Yeah, it would. If you have a certain system of matter, and if you turn everything into its antimatter counterpart, then it will have identical properties from the point of view of things like decay. Okay? So that's as far as we know. Okay? As far as we know, that's true. So it is a mystery. We can't tell immediately by looking at matter far away from us whether or not it's a big hunk of antimatter. However, there is a lot of dust in the universe. When you see the galaxies and the light from stars and all that sort of stuff, it looks, the black areas look empty, but they're not complete. They're not perfectly empty. There is dust floating around, and at least near to us, we have some information on how much dust there is. And if there was a nearby galaxy that was antimatter, that dust would be annihilating with the antimatter. The dust is matter. Right? It would be annihilating with the antimatter and shining light on us that we don't see. So we know nearby that nobody has any reason to believe there are big chunks of antimatter close to us. Yeah.
What is the force, or is it a force that we know otherwise that makes matter and antimatter attractive?
The reason they attract has to do mainly with the fact that the electric charge of the antimatter is always the opposite to the charge of the matter. Right? And so if I've got, if I take my electron for an example, I've got a negatively charged electron, the antimatter partner is the positron, which is positively charged, and we know that opposite charges attract from electrical forces. Right?
So neutrons then would not attract?
That's correct. And a neutron would not very strongly attract an antineutron. Right? Now, it turns out it actually would very slightly. But it's a small effect. It turns out that neutrons are magnetic. And they make every neutron is like a little bar magnet. And if you consider the direction of the bar magnet for an antineutron, it flips its direction, and then those two bar magnets attract. So it turns out even an antineutron and a neutron would attract very slightly. Yeah.
I have a question. So when matter and antimatter annihilate, they do not necessarily give light, right? The energy might not be within the visible light spectrum.
That's true. Yeah, I should say, when I say light, I'm again speaking as a physicist.
Just a clarification.
Yeah. I mean, the light that we see with our eyes is a narrow band of all of the possible wavelengths and energies of light. And I call all that stuff light, regardless of whether or not it's high energy or low energy. So, in particular, let's consider this electron and positron situation. If an electron and a positron, so almost likely right now there's a positron in your body, and it probably got created by a radioactive decay by something in your body. Okay? And what it's doing right now, I'll tell you, it's moving around, and very soon it will find an electron, and it will annihilate. It will make two back-to-back particles of light, and these particles of light are higher energy than X-rays. Okay? So this actually gets to item 3, antimatter in your life. How many people have had or know people who've had a PET scan? Had a PET scan? Oh, very good. Congratulations, you had antimatter in your body. So here's what happened in your PET scan. I'm going to explain it to you from the point of view of the antimatter. What the PET scan was doing was, you no doubt had to be ingested with some nasty stuff. Right? You were injected? Yeah, okay. So, do you remember what nucleus you were injected with? Did they tell you?
Well, you probably told me though.
Yeah, right. Okay, so here's what it was. You were injected with a atom whose nucleus was unstable. Okay? And that atom was in a chemical which was designed to try to go to some specific place in your body. Okay? Then they tried to time the lifetime of this nucleus in such a way that it would decay, it would have enough time to get where it needed to go before it fell apart. Okay? When it fell apart, it made antimatter. Okay? The positron came out of the nucleus. It literally got created. Okay? And that piece of antimatter, very quickly, close by to where it got emitted inside your body, found another electron. They came together and made light, and one high energy, higher than X-ray energy piece of light went this way, and the other went that way. And so then that light has a high enough energy to get outside of your body. Okay? And then you were probably surrounded by a bunch of circular detectors, probably. Okay. what the circular detectors were doing were, one of the detectors would detect one of the pieces of light, the other one on the opposite side would detect the other one, and by triangulating the two locations of the detection, they could tell where it was emitted from. And by doing many of those things, they made a picture of the inside of your body using antimatter. Yeah.
So the antimatter only applies to like atom particles, doesn't apply to like photons, so there is no antiphoton.
Yeah, remember that three-way partition of all the stuff in the universe I was talking about? So we have space-time, matter, and when I say matter, I'm including antimatter. Very confusing way to say it, but that's true. And then there's this third thing, which I call force carriers. It turns out that photons and other things like gravitons, things that carry forces, turns out that in that third group, they don't have antimatter counterparts. There is no such thing as an antiphoton. And there's no such thing as an anti-graviton. For that reason, because it doesn't have the matter-antimatter characteristics, it's possible to hold a piece of matter or antimatter by this third classification of stuff. Okay? Because the touching of the photons to the antimatter itself won't cause it to disappear alone. So for example, people have taken one positron in a very highly evacuated chamber at very low temperature and held it for years. Literally years. They lost it. You know why? They had somebody visiting the laboratory and somebody flipped the wrong switch. And they lost it. It happens, it really does. They were doing an extremely precise measurement of the properties of that piece of antimatter, and they had to hold it for a long time. So back to this question of the universe that you asked earlier. So I said that we can't look at a galaxy and tell whether or not it's antimatter, but we suspect that almost all of the stuff we do see really is matter. Okay? And that is a little bit surprising because there is another thing we know about matter and antimatter, and that is that when we create it in the laboratory, we create equal amounts of matter and antimatter. Okay? So in other words, if I added energy to an electron enough so that it would create other objects, I would start with one electron, and then if I add enough energy, I will make a second electron and one positron. So the new stuff I make is always balanced. Okay? And that's because of conservation of electric charge. There is another interesting thing that's known about the universe, and that is we can count the number of matter particles in the universe and compare it with the number of photons. And it turns out for every proton and neutron in the universe, there are 10 to the 10 photons. The universe, to first approximation, is a ball of light. We are nothing. In the inventory of the universe, matter is almost nothing. It's almost all light. And we do know from laboratory experiments that when matter and antimatter come together, they make light. So here's our suspicion. Our suspicion is that we started from zero, no matter or antimatter. Somehow, in the history of the universe, there was some slight imbalance generated by a piece of the laws of physics we don't understand yet. And that gave us a large amount of matter and a slightly less amount of antimatter. They annihilated, made lots of photons, and we're the ashes. Yeah. So right now, many physicists are trying to search for a piece of the laws of nature that would allow that slight imbalance to develop. Because if we can find the laws that do that, we can explain why it is that we don't have hunks of antimatter in the universe. And that would be super cool.
So it,
Yeah.
I mean, it's not that we don't have the tools to detect it, we just for sure don't see it, or is it like slight chance that we don't have the tools, the proper tools to detect it?
There is a lingering possibility that maybe we're not interpreting things correctly. Maybe there are big hunks of antimatter out there somewhere that are balancing the matter that we do see. That's still an open question. And but I expect that in the next decade or so, that loophole will be closed, probably, because the astronomers are learning where the dust is. Okay? And the dust is predominantly matter. Things, get spewed out in the universe in lots of violent processes, and probably we will know the answer to that at some point in time. My guess is that we're not going to find big hunks of antimatter, but I may be wrong.
So this excess of matter over antimatter, is that percentage something that is easily within detection from Earth down to Earth?
We don't know.
Is it 1 times 10 to the 10th, the ratio is it?
That's right. Yeah, that number is inferred from astronomical measurements. So that number is known. What we don't know is that there is something. So here's our situation. We don't know. We suspect that something about the laws of physics has to be slightly skewed that we don't know about yet to make this observation match reality. We're missing something in our theories. Okay? And so we're searching for what it is, and nobody knows the answer.
Is it possible that it's tied up with the fall of the mass that is not visible?
Could be. That's a subject for another Science Cafe. It's the usual situation in physics. At the end of the 19th century, famous physicists said, "Our subject is done. We've discovered everything." Then explosion, relativity, quantum mechanics, and they were completely wrong. Same thing happened at the end of the 20th century. Oh, we know everything. Now we know that there are these things called dark matter and dark energy in the universe that we know from astronomical observations. They're 95% of the stuff. So everything we thought was everything is now only 5% by weight. So the attitude I take is, well, it's an open ball game again. And who knows what will happen. Yeah.
Could you just sort of go over how does one create an antimatter in the laboratory?
How do you do it? Well, it's not hard. Okay. So if you, here's the only thing you have to do. You have to supply. Okay. So the constraint is that you have to create. If you start from matter and you plow other matter into it, which is what you have available usually in the lab, you have to add enough energies that you can create one new particle and its antimatter counterpart. Okay? So it's just a matter of how much energy you can supply to the object in a reaction. If you add enough energy, you will make antimatter.
But what is the source of energy? Is it like an X-ray or?
There are lots of ways to add energy to particles. We can go up to energies that are much higher than X-rays. And so what historically happened is this is a tale of particle accelerator technology. As technology improved to raise the energy of particles we can make in the laboratory, as soon as we could make enough energy to create an antimatter corresponding to a particular piece of matter, we saw it immediately. And so it's still that way. Every object that we've seen, we can when we supply enough energy to allow the antimatter to appear, it appears.
Are we making antimatter here in Bloomington?
Yes, absolutely. I mean, the cosmic rays that are coming to hit us have much higher energy than the energy required to create, say, a positron and an electron together. So absolutely, there's positrons rattling around in the room.
Well, I meant more like in the laboratory. Do we have like a laboratory dedicated to antimatter study?
We are not doing that here. We, I take that back. We do make some positrons. Okay? They're relatively cheap. Because the electron is a relatively light object, so not very much energy is required. There are a couple of places in the world where antiprotons are made. They're much more difficult. One of them is CERN. I guess there was a movie not long ago that had a scene with antimatter in it. What was that movie? Angels and Demons?
That's right.
Did anybody see that movie, Angels and Demons? Yeah, okay. The movie has an opening scene, which is the experiment apparatus that's trying to make anti-hydrogen. Okay? So they actually show the real apparatus. Of course, the movie is nonsense from the point of view of physics, but they actually show the real thing. So there's only a couple laboratories that can make antiprotons. And the same places also make a few antineutrons. Higher energy antiparticles are harder to make.
I thought I read that maybe the concern that they have anti-helium. Is that easier to make than hydrogen?
Yeah, that's right. I think very recently, so there's an experiment at Brookhaven National Lab in Long Island. What they do is they collide huge nuclei together. So they'll take like a piece of gold nucleus and they'll smash it on a second gold nucleus coming in the opposite direction. And the energy reached in that collision is so high that they make lots of antimatter. Okay? And usually the antimatter they make is such high energy that it comes out as individual antiprotons and antineutrons. But every once in a while they get lucky and they make some of these antiparticles that are close enough together that they bind in small nuclei. And I think it's a true statement that the most complicated nucleus that's been made in the laboratory is anti-helium, which is 2 antiprotons and 2 antineutrons bound together. Helium, the element you may know and love, is 2 protons and 2 neutrons in the nucleus. But that is the latest from a laboratory experiment. It's because they create the highest energy densities per unit volume ever in the lab. So that's the biggest name. Yeah.
So when you're making a positron, you then end up with 3 particles, like 2 electrons and a positron?
Yes, that's correct. Mm-hmm. Yeah, that's yeah.
So you can potentially have antimatter or anti-alcohol.
You could. You wouldn't want to drink it. I want to emphasize that the number of antimatter particles that people can typically make is extremely small. Okay? The antiprotons are essentially made one at a time, almost. Okay? And the amounts we would never be able to get close to making antimatter coffee. That's too many atoms for us. But it's possible. There may be an alternative. Matter of fact, there may be an alternative universe where there's an anti-U. Take all of your matter and turn your protons into antiprotons and your electrons into positrons, and be in some faraway galaxy. There's nothing against the laws of physics that forbids that from happening. And you would function, if you were in an environment where everything else was antimatter, you would have no problem. Yeah?
Why does there have to
Yeah, I don't. I wish I had a good way to explain that, and I don't. It was my item 2 in my list, how it was discovered. To explain that, I would have to explain both relativity and quantum mechanics at the same time. And that's beyond my scope, I'm afraid. So here's the 2 key ingredients. You may know that the theory of quantum mechanics only predicts probabilities for events. Okay? And you may know from mathematical theory of probability that if you include all possible events, the sum of all probabilities of everything has to be 1. Okay? So that's a fact about probability theory, which quantum mechanics is a form of. Then there's another thing in relativity. You may know that in relativity, the time order of 2 events changes depending on how fast you're moving. Okay? If you add those 2 concepts together consistently, you get antimatter. I didn't explain that last statement. But those are the 2 key things that force it to be true. And that's why Paul Dirac was so confident in his prediction, because the conclusion came from such basic features of the theory that in order for it not to be true, very fundamental things about relativity and quantum mechanics would have to be wrong. And that's what gave him the confidence to predict it. So that's about as good as I can do without going in further depth. Yeah?
So did Dirac say anything about what it was about the fire that it gave him this insight?
Dirac was a famously taciturn guy. He would go to conferences and say nothing. I mean literally nothing. He would be very silent, never say anything. And so I haven't researched the history of what he said on the subject, but the only thing I know is that it would fit on 1 page. What he said. He was one of these guys who never talked. And I mean, I know what he was, this business of staring into the fire, it is what happens when you get a flash of insight. You're doing something, you're thinking about, many people have described this process. You're thinking about solving a problem, and then you go, take a shower or walk the dog or something, and you're not thinking about it. And then suddenly, boom, something goes click. And your brain was working on something on the side that you weren't conscious of. Presumably that's what happened in Dirac's case. But beyond that, I don't know.
And what about if you have quarks? You have quarks and antiquarks.
Yes.
So in principle, those could then attract one another and not.
Yes, absolutely. And they in fact do. You can make quark-antiquark collections, and they're unstable because they attract each other and then annihilate and turn into light. So that happens. Yeah.
So you said there is the 1/3 quark and there's the 2/3 quark. So
Yes.
but does 1/3 only attract the 1/3, or can like 2 hetero quarks come together?
I wasn't careful about the positive and negative signs. So in the neutron, there's a down. There are 2 down quarks and an up quark, and I even forgot the signs. One of them is plus 1/3 E, and the other is minus 2/3 E, and so the whole thing adds to 0. And then the anti-quarks, you just take all that stuff and flip the signs, and that gives you the anti-neutron. Yeah.
Do we know that antimatter has the same properties with respect to mass? We've got opposite mass, or if it doesn't, could something like that?
Yeah, so that's, it seems as though mass does not have a sign. We do not know of anything that possesses a negative mass. And so, as far as we know, the mass of a particle and the mass of its, sister antiparticle should be identically the same. That's been checked experimentally to about a part in maybe 10 billion for electrons and positrons. So that's close enough to be equal for us. Yeah.
I'm still having trouble with this concept of matter and antimatter attracting. So
Yes.
if they attract
Mhm.
antimatter and antimatter, why doesn't ordinary matter just fly apart and never make solid bodies?
Okay, here's the thing. Let's consider protons and electrons, okay? Let's do it backwards. Just because two objects have opposite electric charge does not mean they are matter-antimatter pairs. So if I've got a hydrogen atom, I've got my positive proton in the nucleus and negative electron on the outside. They do not annihilate. Okay? They attract, but they don't annihilate. Likewise, the mirror antimatter object, the antiproton with the negative antiproton in the middle and the positive positron on the outside, they don't annihilate with each other. Right? Because they're not matter-antimatter partners. However, the positron is the mate of the electron and the antiproton is the pair of the proton. Those two pairs will annihilate.
That I've got.
Yeah.
But here's matter.
Yes, there it is.
And apparently, this matter is attracting.
Yes, that's correct.
But it would seem that if it would repel if it would attract antimatter, it should repel matter. This is what's hard.
Okay, let me think about that. Attract antimatter and repel matter. It's sort of, let's see how to say it. I mean, matter won't. Okay, let me back up a little bit. The matter you're knocking on, this stuff right here, to a very good approximation, its net electric charge is 0 because the positive charge of the nucleus is being balanced by the negative charge of the electrons. Okay, so if I have an electrically neutral object, it will neither attract nor repel something with no electric charge. Okay? So, for example, say I had a hunk of antimatter in my hand. I've got a magic hand that can hold antimatter. Okay? If this antimatter was, say, antiprotons with no net electric charge because the negative antiprotons were being balanced by the positive positrons, there would be no electrical attraction between this stuff in my hand and that thing. Okay? So there would not be a strong force pulling them together. On the other hand, if I took this matter and separated it into its protons over here and its electrons over here, and if I likewise separated my antimatter into my antiprotons here and my positrons there, then the opposites in these two piles would attract and annihilate.
Okay, then that, I can see that.
Okay.
But then you've already told us that astronomers look for the existence of this because dust particles would be annihilated.
Yes, that's right.
Those are macroscopic. Sure.
Ah, yeah. Okay, so here's, that's true. So what will, it depends on, so what's happening there is the following. What happens there is that, let's turn this table into antimatter now, okay? It's true that if they both have no net electric charge, there's nothing to attract them together. However, it could be that this thing was just moving already towards this hunk of matter. And that's what's going on, is that the dust is kind of flying around, and if the matter if it touches, then things can get close enough that the electrical forces can take over and you can get the combination. So that's the reason that can happen. Yeah.
If nucleic particles don't annihilate ones that are different from each other, like electrons or protons,
Yes.
what would stop the anti-quarks from annihilating each other?
They can. It depends on which ones you're talking about. So, for example, a quark and an antiquark will definitely annihilate. And that means that there are objects that are sort of the analog of atoms that are sort of, rather than being a bound state of a proton and an electron, it's a bound state of a quark and an antiquark, because they have opposite electric charges. Those objects don't last very long, because they do exactly what you say. They come together and then they're gone. But if I have a collection of 3 quarks, none of which is antimatter in nature, those 3 need not annihilate with each other. Okay? So in the proton, I have 2 kinds of quarks, the so-called up quark and down quark. They're different objects, so they don't annihilate, okay? And they're matter. I can have an antimatter version of all these antiquarks. They can bind together. Those things are safe. The third possibility, where the quark and the antiquark bind together, that's the thing that is unstable. So you've got kind of 3 possibilities there, 2 of which are stable and 1 of which is not.
So nuclear fission doesn't always create antimatter.
Nuclear
fission, if like there is a nuclear
fission.
decay.
Fission makes a lot of stuff. It has enough energy to make antimatter. It doesn't often make very much. In nuclear fission, what you're doing is you're taking a very big nucleus and splitting it into 2 pieces. And those pieces typically are very energetic, and they're spitting out lots of particles. And every once in a while, sometimes some of that will be a piece of antimatter.
So what predisposes certain elements to create more antimatter versus some elements which create fewer or less antimatter? Is there like a predisposition, or they all, on average, create about the same percentage?
Yeah, that's a detailed question. There's no... the theory, you can, if you know the details of your forces, you can predict the relative odds of how much antimatter and how much other stuff you make in any reaction.
With that, I'd like to please a hand for Dr. Snow. It was delightful, and we wish we could offer you something more than just applause. Maybe a T-shirt. We're working on a T-shirt, but thank you again, and we look forward to Atomic on Quarks. That would be great.
Happy to talk about Quarks.
And thank you all for coming. Again, I thought it was very, very stimulating. If you'd like to hear more about which ones, we're going to be doing this again in 2 weeks on the subject of Paleo-Indian. So basically, who came? There are various groups that came into North America more than 10,000 years ago. Who came when? This is all kind of in flux right now, this question. And so we're going to have a speaker talk about that in 2 weeks. And then 2 weeks after that, the subject of climate change in Bloomington. What would be the potential impact of climate change in Bloomington by Dr. Ben Brabson? So I think those are 2 very interesting subjects. But if you'd like to hear, just get an email reminder, please put out a list. Leave us your email address. We will use it only for this. Unless someone offers us a lot of money, we will use it only for this. And also, if you have any suggestions for topics, very interested in hearing that. We have a very nice webpage at this point. We're also on Facebook, so let us know if you have any thoughts. But again, I'm going to put this over here. If you have anyone have a pen.